Hello and welcome back to differential equations, section 1.6, which is dealing with substitution method and exact equations. We are still in the first order. We are still looking at equations that are of the form dy dx equals some function of x and y, and we do have maybe initial condition y of x 0 equals y 0. So this is our standard first order linear differential equation, and the solution of this equation depends on, obviously, what type of equation it is, to solve it using whatever method. I did ask you to start compiling on the cover of your notebook, the hard cover, right, the cardboard piece, all of the names of methods and, if applicable, formulas, or maybe one or two sentences on the procedure on how to solve the problem. So some problems some differential equations are solved by using formulas, and others by methods and procedures. So last class we learned the formula for integrating factor, rho of x or rho of t, whatever the variable is. And there was a formula e to the integral of p of x, which you had to memorize, right? There is a way to go around it, but then it's much longer. All right, so what do we have today? Are equations where we are going to use substitution to change appearance of one equation, right? And then once you change the equation using the substitution method, equation might become separable, right? So you take a non-separable equation, use substitution, and then it turns into, let's say, a separable equation. So that will be very beneficial, right? To see and know. And then we'll take a look at other stuff. So just want to pick up a few examples. For substitution method, you guys know, you've seen use substitution, you've seen trig substitution, right? You know there is no formula for it. It is just brute force of doing 5,000 examples to kind of be comfortable in guessing what you are to use, right? It's called experience. So, you know, I don't have any formulas to give you for substitution. We can just, you know, pile up a couple of problems and, you know, hope for the best. It's technically what it is. So let's see. One of the methods is, let me see if I can find something similar so you can practice the one that it's given. These are all spicier cases. Very nice, very nice. Yeah, I'll just go through this one because this one is obvious. So dy dx equals x plus y plus 3 squared. There I say clearly not separable, right? Clearly not separable, because I cannot separate x plus y, which was squared. Yeah, there's plus 3 too, but that's not going to make it better or worse. And because I can't separate this equation, we need to look for another method. So now if you come up with u substitution of x plus y plus 3, then this entire side becomes u squared. But you can't just have u squared on the right. Remember, you still have x and y variables on the left, right? So we have to replace all of the variables. Now, it's important always to understand that y is a function of x, which makes x independent variable. So this is not just u, it's actually u of x. And this is not just y, it's also y of x. So I have u squared on the right-hand side, but the left side is the derivative of y, and y is a function. So if you now express y from this mess, you get u of x minus x minus 3. And now, to find dy dx, you have du dx minus 1. Did this make any sense?
No.
So over here, I have to put du dx minus 1. So welcome to a little bit more involved substitution, right? Some of you might remember back substitution method in Calc 1, where we actually had to express a variable in terms of the substitution and kind of bring everything back in. This is something similar. This y is not a variable y. This y is a function of x. And if I'm taking the derivative of it, it involves chain rule. So when I define a new variable u, which is a new function u, as all of this, so I can simplify it, that u contains function y within. Now on this side, since I am removing y's and I'm bringing u's instead, I have to convert dy dx into du dx. And that I can achieve if I just rearrange this to make it y equals everything else and then differentiate. So here's my dy dx. Derivative of unknown function u is just du dx. Derivative of minus x is negative 1. Derivative of negative 3 is 0. And now you just replace the blocks into differential equation. This block called dy dx, you swap the block what dy dx is, so you snap that in there. This block here, which is this block, is replaced by u, so u squared. Right? What I like to say here, this is like, being a mechanic. See, mechanics do not fix things anymore. They swap parts. I actually know a mechanic who fixes parts. That's a real mechanic. Like all of the new stuff now is they say, oh, your alternator is not working. Here is a new alternator. Doesn't fix the alternator. It replaces the alternator with a new one, right? Also, when your component in a computer dies, right, you replace the whole component. You don't go and fix the hard drive or fix the RAM memory, right? You replace the whole unit. I know this is a new concept for all the Apple users, but for non-Apple users, things actually can be fixed. You don't have to throw them away and then throw away another $3,000 for a $600 piece of garbage. Anyway, so when you do these substitutions, you will always have to define a new function that will be replacing the old function, and you will have to replace that function in a derivative as well. And that can be, in some cases, a little bit trickier to do. Now, this is introductory example, so we can do it in one line. In some cases, it will take you like half a page of calculations just to do substitution, and then you can do differential equation. So now, what do we have? We have a joke of equation. We have du dx equals u squared plus 1. And this is a separable equation, right? It's a separable equation which we can simply solve as du over u squared plus 1 equals dx. We are going to hit both sides with the integral sign. And what do we get? Tangent inverse, very good, of u equals x plus c. Now we know what u is, right? So we are going to say tangent inverse of x plus y minus 3, I believe.
X minus y minus 3. No, it's x plus y plus 3.
X plus y plus 3. So all pluses. Good. Equals to x plus c. And in this case, we can get the explicit solution because we can apply tangent to both sides. So we are going to have x plus y plus 3 equal to tangent x plus c in parentheses. And then we will subtract x and subtract 3 to get explicit solution. Y of x is equal to tangent of x plus c minus x minus 3. And this would be your general solution. We did not have any, this is a general solution. We did not have any initial condition to calculate c, so we are done, right? If you have initial condition, you still have to go in and deal with this stuff. Cool. So that's one example. Let's do another example that will be a little bit more involved. So that was introductory. Let's see if I can find something from homework. Again, I don't like working out exercises that are done in a book because you can read those. I like extra examples. Let's see if we can do anything with problems. Any one of these is... here is the one that looks disgusting, but it's somewhat obvious. Problem 8. X squared y prime is equal to xy plus x squared e raised to the y over x as the exponent. Right? So this is one of those problems that you can just go and say, look what I can do. For no reason. Now, you're staring at this and you go, wow, right? But there is one feature that really screams off of this example. You try and guess. So what is the one thing?
Y over x.
You're close. Something in here could provide the substitution, right? If we need to line up more ducks in order for everything to work, but there is a feature of the entire problem that jumps out a little bit. And that would be, just make a wild guess. Y over x. Very good. This exponent over here is an interesting feature, and it is an extremely common substitution, right? If you're going to tattoo anything, tattoo u equals y over x. That's, u equals y over x is a good tattoo. Now, we are not ready to use this. I need to do some more work. So we see a lot of these x's floating about. So we're going to divide by x squared and also state that x should not be 0 because we divided by 0, right? So when I hit, now use different color or copy equation again when you are dividing original problem. So if you don't have different colors, copy the equation and then divide everywhere by x squared. Our new equation is dy dx equals y over x plus e to the y over x. Oh, now it's clear that our substitution should be y over x, right? Because you have this y over x reoccurring, right, multiple times in the problem. So once you do this initial division or whatever algebraic, right, magic you have to pull off on the first step, substitution might reveal itself to you. And in this case, here it is, and that's why we pick that. So it's not arbitrary. Now, in some cases, it's not going to be this, and then you have to try a couple of things, right? You try, and then it fails, and then you try again. You modify it a little bit, right? It's the way this thing works. Just like your U sub and your trig sub and all of the problems you learned before. This is a substitution method. There is no formula for it. So technically, this is me telling you, good luck. Yes?
Could you solve this using the method we used last class?
No.
No?
No. You want to use integrating factor here, it's not going to work, unfortunately. So, here we go. We have our U sub, and now I need to come up with a du dx, right? Because once I find du dx, that du dx will contain somewhere dy dx, which is something that I have to substitute. So what I have here is now a quotient rule of a function y of x divided by linear function x. Quotient rule is x squared in denominator, copy x, and here is your dy dx over here, minus y. Quotient rule from Calc 1? I hope we are still all in the same truck. Yes?
Could you solve for y and then the y instead?
Yeah,
Yeah.
you can. Actually, that's way better than what I did. It's so much better that I'm just going to completely erase what I did and solve this for y as u of x times x and then do product rule. This is where all of you turn and say thank you.
Thanks, Ivana.
See? Okay, we have two nice people and the rest of you are terrible. Now, when I find dy dx will be a product rule. Copy the first derivative of the second plus copy the second derivative of the first. Awesome. Now, we bring all of these features into our differential equation. Dy dx gets replaced by, actually, let's do it this way. U plus x du over dx equals, this over here is just u plus, and this one is e to the u. Do we all see these substitutions? Meditate on this a little bit. Now, I am going to subtract u on both sides. That will cancel the u's. And once the u's cancel, I have x du dx is equal e to the u. We are ready with the basic separable equation, right? I have du and then e to the minus u in front. You can write du over e to the u, but we'll be integrating, so just put the e to the u upstairs and put a minus, right? On the other side, we have dx over x, because dx will be multiplied and then x goes in denominator. Hit both sides by the integral sign. We are going to have negative e to the negative u equals ln of absolute x plus c. And now we will put the negative, right? So the whole equation times negative 1. I'm going to have e to the negative u equal negative ln absolute x. And then I put plus c, and some of you will be triggered because I didn't distribute negative to c. But we did talk about differential equation plus c absorbing constants and signs and so on, because we get to compute that with initial condition. So even if I had to divide both sides by negative 2, it will still be plus c instead of negative c over 2, right? Now I am going to ln both sides. And this is where we are going to kill that e. Now on the right-hand side, we're going to have ln of 1 over x plus c. I'm going to write, I know I wrote this formula the last class. I'm still going to write it. ln of x to the p is equal to p ln x. P was negative 1 in this last line. That's how this negative changed x into 1 over x, right? Because the exponent of negative 1 is just 1 over the value. Now I have a negative sign in front of u. That's going to get multiplied into, to get rid of that one. So that's going to be u equals negative ln of 1 over x plus c. And now for u, we know u was defined as y over x or x over y? Y over x, right? So y over x is equal to negative ln 1 over x plus c. And you just multiply this x to the other side. Y of x is equal to negative x ln of 1 over x plus c. And this is known as your general solution, because they did not provide any initial conditions. Actually, the first 30 problems in your homework do not provide initial conditions at all. Yes?
You see how you did the negative on the outside originally? Can you do that again? Or no?
Yes, it will create a double fraction, so I don't want to. It's going to create for computer science more operations, which would make software less efficient. So can I put positive ln and then just add the whole parenthesis 1 over? The answer is yes, but I don't want to, because it actually makes it worse. You are introducing double fractions, and that's why. And you're probably going, this is really inconsistent. Yes, it is. We care about efficiency. Do we need another one of these examples? Yeah, why not, right? What else are we going to do? What was that? Say no more. There's just one trig example. Like in a whole 30 problems, is one trig example. And I see counter of you like, no, please don't. Please, no. One trig example, that's it. We can do that, or we can do something worse.
What's worse?
Because trig always simplifies nicely. You are guaranteed to have a beautiful problem. Here's trig, right? But then you see something like this, and then you understand what I'm talking about. All right, you're gonna love this. Let's go. How about problem 13? Lock the doors. X times y prime equals to y plus, everyone's like, yep, easy, square root of x squared plus y squared. It's time for you to talk to people around you, right? Behind you, in front of you, and try and figure this out. This is what your exam question looks like. This is your exam 1. Solve. Well, I'll add a couple of more. But there is nothing, right, weird, special about this problem. So your exam question, solve. Done, right? Go ahead.
So do you think u is x squared plus y squared?
Probably not.
No?
It's the grade even, yes. Yes.
Square root of x squared plus
So, yes.
Well, no, that u is going to have to be a function inside of another function, so it would be something inside of the square root, but I'm not sure.
So wouldn't that make it x squared plus y squared?
I mean, I guess so.
So,
Is it?
whoa, right?
Are we supposed to do that?
No, you have to talk.
Ah, shit.
Yeah.
I don't want to do any of these.
Fair, but see necessary.
How are you starting that? What are you making here u? I don't know if it should be x squared plus y squared.
I think we're doing multiple variables, kind of like how you have multiple functions. So you break down the root x squared y squared into 1, and then you take a whole variable into the second one.
Okay. I don't like that.
I don't like that either,
But I think that's what he wants us to go with.
Probably.
Well, it is a circle.
I am bad on giving legal advice because you know me.
Yeah, it's a circle. It's a circle. Square root of x squared plus y squared equals r squared equals r.
something cool.
Aldana always does something cool.
That's what caught my eye first. That's what it was. It was
Yeah, that's
pretty
what I
sure.
wanted people to listen today.
I think we're integrating a circle. That's what it was. The area of a circle.
Yeah. Or she got it already.
Okay. Well, yeah, she's so smart. That's why I ask her.
No, this is one I say I'll let the biologist to show you how it's done.
Yeah.
All the math majors like, what? I like showing engineers like, what? A bio major got it? I'm not gonna sleep for next month. Mathematical biology is one of the scariest mathematical fields today. And mathematical biology doesn't happen until you hit like PhD level. So that's
Well, we have
how-
our y over
that's
x
how
now.
insane it is.
What did you do?
Divided it by x.
Systems of coupled
Oh.
differential equations to
That's what she
describe
said.
neural
Divided by
networks.
x.
I squared
Biological
everything here
systems
in
are
square
the
root.
most complicated things that we know of on the planet. Everything else is less complicated. The only things that are not mathematically mapped are human bodies because it's so complicated. So you have various groups of professors of various universities mapping small portions of the brain and so on, right? Everything that is mathematically mapped is easy for us to build, including cell phones, computers, and then we can fix them as well. For humans, what are we doing? Trying to guess a medication for cancer. because mathematically the body is not mapped, and because the body is not mapped, you can't create a machine or something that, right? So if, as I said earlier, if a component dies or something like that in a computer, you just swap the component because you can make another one, right? For a human body, it's virtually impossible right now. But you have a lot of professors at MGIT and other universities that are mapping out. And then once they map things out, then they can 3D print them and create 3D printed organs and all the other things. So Google had this initiative and idea that we will make humans immortal by 2052. But by 2052, so no matter which organ fails, so I can just 3D print another one, plug it in, like you would plug in a RAM memory, right? But and 3D printing organs has been around for 10 years at least. There's a TED talk on it. If you guys like TED talks, you can go one and look for 3D printed organs. And a TED talk is the kid that actually has 3D printed organs. He is part of the presentation. And they are trying to make some of the vital organs actually live and work past a week or a month, right? So it's a lot of research and a lot of development and a lot of mathematics going into that. Some of the systems that I've seen have like 20 parameters in it. You have A, B, C, D, E, F, G, and then you have to kind of tweak each one of those numbers until you behave exactly as logical, right? And because they're so individual,
I wish we could talk about it. It's interesting.
I'm listening.
All of that into right then, because one treatment works for one person, the same treatment doesn't work for a different person. It's the same condition. It's very, very touchy. So it's one of the areas that mathematical balance. Yeah, so these are the things that you would see in
These are the lines.
so mathematics at the graduate level. I'm trying to figure theory, which is pure mathematics.
Yeah, so I don't. So I think that's mainly
Facebook does, like they like the numbers and the Fermat theorem and all these kind of things. Just theoretical mathematical results. Eventually, you only use them one. Problems, problems about price and so on, they're mostly there. So that's theoretical mathematics and game. Then you have statistics and probability. Then you have applied math. You got fluid differential equations. You have waves, also differential equations. And then you have biology. And you go into one of these tracks. There's also a track, a very small track for economics and finance to work. With UN or some global organizations, right? You want to become accountant, you're becoming a professor. Understand the economics on the global scale, and then you can do Wall Street and these kind of things, which is huge, stochastic mathematics. So those are the branches of mathematics you can apply yourself along those tracks. Or you can use one like me. Is that too, right?
I don't think you
Become fat and no hair. This is what we call Would you like to present your solution? Oh, so differential equations are no issue, right? Hell breaks loose when we have to figure out the inverse tangent. I see how it is. Yeah. All right. Generally, when you are faced with a substitution equation or just an equation, try to isolate y prime, right? Which is what I say, just remove the garbage, right? So whatever is multiplied into y prime, try to get rid of that, see what you get, and maybe substitution would reveal itself, right? So in this case, I'm using a different color. I'm going to divide everywhere by x. When I do that, I get my y prime, which I will call dy dx because awesome notation from Leibniz, right? And then I'm going to have my y over x. And then when this x undergoes the square root, it will pick up a square. So I'll have x squared over x squared plus y squared over x squared. One line to simplify this little bit to make our life better. And we get 1 plus y over x, everything squared. And at this point, I need to make sure that we all know what the substitution is by looking at the problem for 2 seconds. Right? It is y over x, right? So we have the same substitution of u equals y over x, and then y is ux, and then dy dx is the product rule. So u plus, right, when you copy u, the derivative of x is 1, and then copy x, and then du dx. Replace everything into your differential equation. Did I say this is problem 13? Yeah, good. So this is a problem 13 from your homework. And plug everything in, so we get u plus x du dx is equal to u plus square root of 1 plus u squared. Are we all green here? Perfect. Minus u will drop these u's. And I have x du dx equals to the square root of 1 plus u squared. Yay! Separable equation, right? We have du divided by the square root of 1 plus, lock the doors over there, equals to dx over x. All we need to do is what? Compute. Good. What's my integral on the left? It cannot be inverse tangent because it has a square root, right? Yeah. But you are so close. No.
It's a trig function.
It's a trig substitution. Very good. So here is your trig sub. And here is your ln of x, right? You're done.
Here is the trig sub.
Wait, did I mention at any point that Calc 2 is a prereq for this course? So yeah. I said eventually you're going to run into trig sub, so why not now? For a trig sub, we draw the triangle.
Yeah.
And then, yep. And then you have your u and your 1 and the square root of u squared plus 1, if this is theta. And then we make our sines and cosines towards the constant, right? So tangent theta is given as u over 1, which is u. So u equals tangent theta, and du equals derivative of tangent is? Very good. D theta. So we have that part. And then we also have the cosine, which will become secant. So cosine theta is equal to 1 over the square root of u squared plus 1, from where the square root of u squared plus 1 is equal to 1 over cosine theta, which is secant theta. So our integral is, instead of du, we have secant squared theta d theta, and in denominator, instead of the square root, we have secant theta, and then this is equal to, on the other side, we have dx over x, which is ln of absolute x plus c. Left-hand integral is secant theta d theta, which is equal to ln of x plus c. And the integral of secant theta is
It's going to be the substitution with the tangent theta because it's secant plus tangent.
That-
Secant plus tangent.
you actually remember the
No, because I did like that one. Yeah.
that's amazing. Wow. Nice.
Then it becomes
ln secant theta plus tangent theta. That's exactly how you do it. I'm actually very impressed. Very good. Very good. Now, guys, I have ln equals ln, but then I have this dreaded plus c. So I'm going to now pull another trick out of my sleeve, where I'm going to write this c as ln of e to the c, because I can, right? Now, why do I do that? So that I can have ln of x plus ln of e to the c. And what does that do? You can combine, right? Combine into ln x e to the c. And then you have ln of secant theta plus tangent theta is equal to ln of x e to the c, like this, or e to the cx, whatever, that's a constant. You can define e to the c like capital A if you have no objections. For some reason you like A, so that's fine. This allows us to just drop ln's. So if you mush together the right side into a single ln, then you can drop ln's from both sides, and just have secant theta plus tangent theta equals ax, where a is e to the c. Now, no one cares about theta. We gotta go from theta to u, and then from u to y, and then we're done, right? Now, luckily, we have our triangle, right? We know that the secant is square root of 1 plus square root of u squared plus 1 plus, and we know that our tangent theta is just u equals ax, right? If we use the triangle. And then we also know that u is y over x, right? So here's our y over x squared plus 1 plus y over x equal ax. And this is where you box and leave it, right? General solution, implicit form. You cannot write this solution for this problem as y equals everything else, because go ahead, ruin your day. You'll get nowhere, but at least you tried and learned all the ways in which it cannot work, right? So some solutions in differential equations will be implicit, which is this. You cannot write it y equals everything else. Your previous solution was what we call explicit, y equals everything else. Right? Welcome to DIfeq. I think we beat this one to death. Right? We did 3 examples. You have 30 examples to practice in the textbook. A couple more examples done in a text, so you can read those and review. We are going to now switch gear and talk about exact solutions, exact equations, which is something we did in Calc 3. Now we're learning this from scratch. So if you didn't have Calc 3, you don't have to panic. But we are going to need partial derivatives from Calc 3 to survive this technique. So hopefully you know your chain rule well, so we can survive through that process. So part 2 of today's lecture here is on exact equations. Now, if the exact equation is given to you in a form you can immediately recognize, you just execute exact equation procedure. This is a really weird notation. You have a multivariable function m multiplied by dx plus multivariable function n times dy. This can be done in any dimensional space. In Calculus 3, we have x, y, and z there for throw-dimensional vector fields and so on. So you can do this in 7 dimensions if you want to have 7 of these x, y, z, w, and so on. Now, this is the form, and then we have a condition for exactness. Equation is exact only if the condition holds, and the condition is that the partial derivatives have to be the same. You must check that every time, unless the problem says use exact, right? In that case, clearly it's exact. But if you're staring at the problem, trying to use this, and it's not exact, you will get a solution, which would be a garbage solution. This is one of those scary problems in mathematics that you can do, it looks good, you get a solution, it looks good, no hiccups along the way, but it's garbage, all right? And the reason was the equation was not exact, so solution you got has nothing to do with anything, okay? So you have to check. So you're not only memorizing equation, you're also memorizing condition for exactness. Partial derivative of m in respect to y must be the same as partial derivative of n in respect to x. And you put the red box around, and I'm going to write in blood condition for exactness. Criterion, they say in the book criterion. Condition, criterion, can care less which word you're going to use. So, as I said, it is very easy to spot these problems if they are given in that form. Let's find something that is not going to trigger you. 34. 2xy squared plus 3x squared in parentheses dx plus open parenthesis 2x squared y plus 4y cubed dy equals 0. I hope you see your m and your n. Are we all green there? Good. Since not all of you have completed Calc 3 yet, even if you're taking Calc 3 now, you are still not, you haven't reached partial derivatives yet. That's 2 chapters away for you now. Partial derivatives only care about the variable that is the main variable for that derivative. The first condition says that your derivative is in terms of y. The second over there is in terms of x. Now, when you are taking partial derivative in respect to y, all of your x's are constants. All of them across the problem. So you will either copy them, or if you have a term that only has x's and you're differentiating in respect to y, that term just dies. Because there were no y's, there are no variable in that term. So the whole term is constant and it's just 0 in a derivative. So those are the two things you have to be careful with if you never did partial derivatives before. So now I am going to calculate partial derivative of m in respect to y.
And it equals 4x y plus 0.
Great. So I am taking the derivative. The partial derivatives have this squiggly d. It's not a straight d, it's a squiggly d. So partial derivative of 2x y squared plus 3x squared. Now, my variable is y. This puppy here is the variable, which means this is the 2x is a constant. So I will copy 2x, and then I will take the derivative of y squared, and derivative is 2y. Plus big fat 0, because the derivative of 3x squared has no y's in it, which means it's constant. Derivative of constant is 0. So the derivative is 4xy. Cool? Partial derivative of n in respect to x, same thing. We have a partial derivative. We are going to copy the function 2x squared y plus 4y cubed. And now, partial derivative here, remember, y is a constant, so 2y is a constant you copy. Derivative of x squared is 2x plus another 0, because this term has no x's, and x is a variable, right? Because you're taking partial derivative in respect to x. So if you're taking partial derivative in respect to x, x is a variable, y is a constant. So this one has no variable in it, therefore it's 0. 4xy. 4xy equals 4xy. Criterion for exactness is satisfied. So this is an exact equation, and we can unleash the procedure for exact equations, which is coming up. All right? Sounds good? So we're all cool with the condition. This has to be your first part. So, on the exam, part A, is this exact equation? You crank these two lines. Part B, if it is exact equation, solve the equation. I just want to make sure, so they're using just m and n, and they don't have, because the book I learned from is using phi for potential function. Calculus is also using phi, and these guys magically use capital F, so I have to keep the notation. All right. Ready? To solve this differential equation, you are going to pick, let's say m, right? And integrate that one to get your partial solution. And then you are going to fix that solution in one more pass, and that's where you get the solution for the differential equation. So it's going to be a two-step problem, just like in Calc 3 for potential function. It's exactly the same calculation. It's just we are using different notation. Over there is called potential function and conservative vector fields. Over here is called exact equations and condition for exactness. Same calculation, 100%. So we are going to pick the function m and integrate in respect to x, right? So I'm going to say that my f of xy, which is the solution to my differential equation, is going to be equal to integral, I'm just going to do m dx, so you know what I did, which is integral of 2xy squared plus 3x squared dx. Now, x is a variable. Just integrate. You know how to integrate, right? F of xy is equal to x squared over 2, so it's going to be x squared y squared, plus x cubed, right? Because it will be x cubed, plus c as a function of y. Ooh. What do you mean constant is a function? Welcome to partial derivatives and partial integrals, okay? Would you agree that if I take the derivative of this in respect to x, that would die? Even if it was like y squared, or e to the y, or tangent of y. If I'm taking derivative in respect to x, this could be 0, could be number, or could be any function of y you can possibly imagine. The derivative in respect to x would kill it equally, right? So it could be some function of y. I cannot limit this only to be a number, right? And this is the only time in differential equations when you will have plus c of y. All others will just be plus c. So again, I have a partial derivative. I have to integrate partial derivative. When I integrate partial derivative, remember, partial derivative ignores the other variable. So if I integrated partial derivative in respect to x only, and I can only integrate in respect to one at a time, that integral will give me the function plus a constant, but since it's a partial derivative of x, that constant could also be a function of y, which is why we have for the first time constant as a function of y. Now, this is your partial solution. Part one of the thing is done. Now, the second step. The second step is we need to do this one more time. And the way we're going to do this is we are going to now take the partial derivative of this problem in respect to y and equal it to the partial derivative of y to check the terms. It's confusing, but when you rewind, it will make sense. I'm going to find the partial derivative of f in respect to y, which would be 2x squared y plus 0 plus some c prime of y unknown function. And I'm going to equal that to the partial derivative of y, which is capital N. So, oh, come on, pen. So put this equal to n, capital N. So you will set this equal to n, because n is a partial derivative in respect to y. And you took partial derivative in respect to y from the function here. So now you're just equaling those two partial derivatives of y to each other. So, and our n was what?
2x squared y plus 4y cubed.
Plus 4y cubed. Thank you very much. Nice. So from this, I am extracting that 2x squared y, I guess I have to replace the battery in this thing, plus c prime of y is equal to 2x squared y plus 4y cubed. What have we learned?
That c prime of y equals 4y cubed.
C prime of y is equal to 4y cubed. Can I get my c of y out of there somehow?
You can integrate it.
Beautiful. Integrate both sides in respect to y. So c of y is, when I integrate this, y to the fourth plus constant k, right? So y to the 4 plus constant, say k or capital A if you don't like it. So now I have a c of y. Go to your partial solution and stick it in. So f of xy is equal to, we're copying the whole problem, so x squared y squared plus x cubed I'm running out of ink in a pen, so it won't write. There we go. Plus x cubed, I said, plus y to the 4th, and then plus k, and usually we say equal to 0. So what is your solution to the differential equation? It's the implicit, right? Say equals 0 here. So it's implicit solution x squared y squared plus x cubed plus y to the 4th equal k. I know you're going to get triggered when I move k to the other side. It should be negative k. Yeah. Because it's going to be absorbed by k, that negative, and then you have initial condition, you can compute the k.
Wait a minute, I got a question.
Mm-hmm.
Wouldn't the one side either be negative?
What do you mean?
Well, if you're putting k on the other side, won't you have to like...
That's what I just said. Right, that's what I just said, because it gets absorbed. We never care about the sign of plus minus c, plus minus k. Even if you multiply it by 2k or 2c or c over 2, we just write plus c for all of them. Because that value will be determined if you have initial condition, right? And if you have it on this side, it will be negative 3. If you have it on this side, with positive 3. Doesn't matter. Just dump it there, and then and your MyMATLAB better accept it as positive k there. Yeah, I know. I've seen it. We sat together and went through that problem 3 times to fix it. All right, now we have a solution, right? And I said, this problem, we already had it in a form. What do I mean had it in a form? Well, it was of the form m dx plus n dy equals 0. That was the form of the problem. What would that problem actually look like as a differential equation? Which problem we did? We did
34.
34, thank you. You know what this problem looks like? Well, the book gives it in the proper form. But this problem can as well say y prime. Yeah, my ink is done over here, as you can see. Y prime equals to negative 2xy squared plus 3x squared divided by 2x squared y plus 4y cubed. This is what differential equation might look like, right? When would you think to use the exact equations? Well, when all other methods fail. Because you tried substitution, clearly doesn't work. You tried separation, clearly doesn't work. Integrating factor, right? You can't put in a form to have your p and q. So if you can't put in a form to have a p and q, you can't solve the problem using integrating factor, right? then you try substitution and quit as well, right? Once you write this as dy over dx and cross multiply, very good, you get the form of, right? So it's good thing to say in parentheses here, if the problem looks like this, use the Leibniz notation dy over dx, cross multiply, you will have it in exact form. Check the exactness condition, and then if it's exact, right, if the partial derivatives are the same, unleash the partial derivative. Let's take a look at one more example. We have 20 minutes, so it should be enough. Because I want you to enjoy this first, and then we'll deal with it. Now, I heard that, so we will make sure. So your classmate ordered the trig, so here we go. Y prime equals to negative, well, there's a negative here, right? Negative cosine x plus ln y, and then you have x over y plus e to the y. A little bit of everything, right? Exponential, logarithmic, trigonometric, and some of the polynomials. Put that all in a mix. So your job is first to transform this into the exact form, check the exactness, and then hit with the partial derivatives. I mean, partial integration with the c of y and so on. Let's go. 18 seconds.
Interval of ln y through d. Right?
Yeah, because we're treating this as a constant.
Yeah.
Just delete.
What do you mean?
What?
Does it come out to be exact?
Yeah.
Yeah.
Because partial m
Did you
over
forget how to
partial
take partial
y is
derivatives?
1 over y.
They should both equal 1 over
1
y.
over y.
That's how math works. No.
All right, let's take a look. We write it as dy dx and separate and all of that stuff, so it should be x over y plus e to the y times dy equals negative cosine x plus ln y dx. Then we move the term to the left, becomes positive, so cosine x plus ln y dx plus x over y plus e to the y dy equal 0. Here's my m, and here's my n. So now we have exactness condition, partial m, partial y. Partial m, partial y is partial y of cosine x plus ln y. Isn't that just 1 over y? Because the cosine x has no y in it, so it's just 0. Partial n, partial x is, partial respect to x is x over y plus e to the y. Also 1 over y, because the derivative of x is 1, and 1 over y is a constant. So 1 over y times 1 is 1 over y. Plus 0, because e to the y has no x in it. It is constant in the eyes of x. Therefore, derivative is 0. So there we go. Exact. Right? Which means we can pick. Now, you choose the way you want to start the problem. Do you want to start with the m and integrate in respect to x? Or do you want to start with n and integrate in respect to y? I don't care which way you start, right? So if you want to start with let's say n, you would have to integrate in respect to y, and then take the partial derivative in respect to x and set it equal to m. If you start with m, then you will get the solution and then integrate in respect to y and set it to n. I don't care which way you do it. So what should I do? M or n? M. Okay. So we start with the integral of m. Oh, sorry. F of xy, which is our solution, is integral of m dx. That's integral of cosine x plus ln y dx. When I integrate, I have integral of cosine is sine x plus x ln y. Beautiful. Ln y is just a number when I'm integrating in respect to x. So I just integrate in respect to x, and I just get x ln y plus c of y, because the function could be, right, could be some kind of function. Last time was a function. So this is my f of xy. I'm going to lightly box this because this is a partial solution. It's not a solution, but it's already almost a solution.
C prime, right?
No, just c. Now we're taking the derivative becomes a c prime. Now we are going to hit this with the partial of y, becomes partial f, partial y, and sign dies. This becomes x over y plus c prime y, because the derivative of c of y in respect to y is c prime of y. We set this one equal to n, which is the partial derivative in respect to y, and n was given as x over y plus e to the y. So now when you compare these two because they are equal, you will get that x over y plus c prime of y is equal to x over y plus e to the y. What do we learn from this expression?
We get rid of the
E to the y. We are going to hit both of these with the integral of y, and we are going to find that our c of y, because derivative and integral will cancel. That's your fundamental theorem of calculus, right? Derivative cancels the integral. So we have our c of y is equal to
E of y plus c.
e of y plus k. Right, c is already in the problem. And now we are going to import this in our solution f of x, y, which was, I believe, sine x. What was it? Sine x
Oh, it's a sine x plus x ln y equals
x ln y
plus
plus c, which is e to the y plus k. And then we write our explicit solution. Right, you say equals 0 here, right? So,
equals k.
the pen doesn't work. Sine x. I wrote every expression 2 or 3 times. Yeah, the battery is dying, so I'll replace it.
Well, I have mine.
Equals k. There we go. Class is over. Thank you. You're nice. This over here, look, it's when it stops. This is what do we call?
The explicit solution.
Yeah, I wouldn't. Would the pen work like without? No, don't
I
think
don't
about
know
it.
if it works for Lenovo. It doesn't work for.
That's what I wanted to check. It doesn't.
No.
This is your general solution because we don't know k. But if you have the point, you will plug in x's and y's, and you will calculate the value of k. So this is called general solution.